that shape our world, and you want to do it without drowning in a sea of raw data.
Right, the information overload is real.
It really is. Well, you are in exactly the right place. Today, we've built a custom deep dive just for you. We are unpacking the actual mechanics of how the modern built environment comes together.
And specifically, how it comes together without falling apart.
Right. We're looking at a fascinating short article, really an excerpt, titled Beyond the Punchline: BIM and the End of Construction Surprises.
Which is such a great title because, well, it's brief, but the source material is just incredibly dense.
Oh, absolutely.
It's packed with industry-shifting concepts about building information modeling, or BIM. And what we're really talking about today is this massive transition.
From what to what exactly?
From relying on, on-site heroics and improvisation.
Well, just figuring it out in the mud.
Exactly. Moving from that to demanding absolute digital certainty before a single shovel even hits the dirt.
It's a total paradigm shift.
It fundamentally restructures the risk, the timeline, and honestly, the culture of how we build the modern world.
To really frame this shift, the excerpt uses this brilliant, relatable metaphor. It revolves around April Fool's Day.
Which I loved.
Right. Now, on April Fool's Day, a harmless prank is great.
Sure.
Finding a fake plastic spider in your coffee cup.
Or someone swapping the sugar for salt.
Yeah, exactly. You take a sip, it's gross, it's a quick laugh, nobody gets hurt, and life moves on.
Right.
But when we pivot to the world of heavy construction, the absolute most expensive joke in the world is discovering a massive design error right in the middle of a live physical construction site.
That is the core friction of the entire industry.
Okay, let's unpack this.
Yeah.
Because the specific scenarios mentioned in the text really paint a vivid picture of this traditional chaos.
They do. Anyone who follows large-scale development knows about the sheer spatial density of modern buildings. They are packed tight.
So imagine this for a second. Imagine you're on a massive commercial project.
Okay.
On the 2D blueprints, everything looks fine. It all seems perfectly viable. But suddenly, you're on the physical site, and the team realizes a massive HVAC duct has been designed to pass confidently, just straight through a solid load-bearing steel beam.
Oh, man.
Yeah, or consider this one, a heavy water pipe, right? It was drawn up by an entirely different team of engineers.
Working in their own little silo.
Exactly. And this water pipe decides to occupy the exact same physical space in the ceiling as a high-voltage electrical cable tray.
Which is terrifying, really.
And expensive. Another scenario from the text is a massive structural concrete column appearing exactly where a doorway was supposed to be.
Just blocking the whole hall.
Right. So why does this keep happening in traditional workflows?
Well, it highlights the inherent flaw in relying on two-dimensional overlays to solve three-dimensional problems. Historically, the architectural team, the structural engineers, and the MEP contractors.
MEP being mechanical, electrical, plumbing.
Right, the MEP guys. They all operated in total isolation. They generated their specific flat drawings completely independently.
So they aren't talking to each other.
Not really. And then attempting to manually overlay dozens of complex static 2D plans and just visually spot where a pipe might hit a cable tray.
It's impossible.
It is. You're asking the human brain to process millions of spatial data points all at once. Fatigue sets in, and those clashes inevitably slip through to the field.
And the fallout is brutal.
Staggering. When a mechanical contractor finds a beam blocking their ductwork, they can't just bend the steel.
No.
They can't just route around it without a massive cascade of consequences. The whole operation grinds to a halt.
Right, because you have to file a formal request for information.
The RFI, yes. Engineers are pulled back in to redesign the pathways on the fly.
All while extremely expensive construction crews are just left standing idle.
Burning through the labor budget by the hour.
So what starts as a funny little mistake on paper, a missing line, mutates into an absolute nightmare in reality.
Materials are wasted, schedules are blown, the costs skyrocket.
It's so easy to see why finding out your design doesn't actually fit together is the most expensive joke out there.
Absolutely. And that brings us to the paradigm shift. Enter BIM.
BIM, Building Information Modeling.
Right. The core function of BIM is to systematically remove that punchline.
It changes the battleground.
That's a great way to put it. Instead of waiting for all this spatial chaos to happen in the mud of a physical site, BIM shifts the entire conflict into the digital realm.
Before a single shovel hits the dirt.
Exactly. You are effectively building the structure twice, once in data and then once in dirt.
The text mentions three massive interconnected tools that make this possible. The first one is model-based coordination.
Right. And we are moving far beyond just basic 3D geometry here.
It's not just a nice rendering.
No, the entire project is constructed as a highly detailed, data-rich digital twin. Every structural beam, every piece of conduit, every mechanical route is integrated into one central model.
Testing every single piece digitally.
Yes. That centralized model becomes the single source of truth. A digital duct isn't just flat lines on a screen, it's a parametric object.
Meaning it has actual data attached to it?
Exactly. It knows its precise dimensions, what material it's made of, and its spatial coordinates relative to everything else in the building.
Which sets the stage for the second massive concept, rule-based clash detection.
This is the game changer.
This is where the computer does the heavy lifting.
Yeah. The system doesn't rely on a guy just scrolling through a 3D model hoping to visually spot an overlapping pipe.
Because you'd still miss things.
You'd miss a lot. Instead, the software is programmed with specific algorithmic rules. It automatically scans the entire database and flags the exact coordinates where two objects are trying to exist in the same space.
It just automatically tells you, hey, this pipe is hitting this cable tray.
Right. And it's nuanced, too. It's not just physical intersections. The rules can factor in necessary clearances.
Like what?
Well, say a pipe isn't physically touching a wall in the digital model,
Okay.
but the software knows that specific pipe requires 2 inches of thermal insulation around it. And it needs another 3 inches of clearance, so a worker can actually fit a wrench in there to install it.
Wow, that's incredibly specific.
It is. The algorithm detects that clearance violation and forces the design team to fix the spatial conflict virtually.
It's basically a digital time machine for a skyscraper. It turns potential April Fool's disasters into early-stage design intelligence.
Exactly.
And speaking of time machines, that leads perfectly into the third tool, 4D simulation.
Right. Building the spatial model is one thing. Adding the timeline is an entirely different level.
Adding the element of time and schedule before construction even begins.
Yes. Time becomes just another geometric property. 4D simulation links the project's complex schedule directly to the physical objects in the 3D model.
So you aren't just looking at the finished building.
No, the team can watch a digital simulation of the building constructing itself chronologically.
Hour by hour.
Hour by hour, day by day, based on the plan schedule.
Okay, so let's say I fast forward to month 6 of the project.
Sure.
I analyze the site, and I realize a massive crane is scheduled to lift HVAC units onto the roof on Tuesday.
Okay.
But the simulation shows me that the perimeter wall the crane needs to drive through was scheduled to be built the week before.
A classic scheduling conflict. And identifying that logistical bottleneck digitally lets the team restructure the sequence.
They just changed the digital schedule.
Right. They delay the wall or they move up the crane operation long before any real equipment is ever mobilized.
The implications of having this kind of well-coordinated BIM environment are just wild.
They really are profound.
The excerpt breaks down 4 very specific operational outcomes of this. And I really want to spend some time letting us thoroughly unpack these because this is the real meat of the transition.
Let's do it.
Point number 1. Hard clashes are detected before procurement.
Procurement meaning buying the materials.
Right. And for a complex project, procurement isn't just going to the hardware store for 2x4s.
No, we are talking about custom fabricated, highly engineered components.
Like a 50-foot custom steel truss.
Exactly. Or a specialized glass curtain wall. It's manufactured to the exact specifications of the design.
So if you discover a hard clash on a physical site, you've already bought it.
You've bought it, you've paid for the custom fabrication, you've paid to transport it on a massive flatbed truck, you've paid a rigging crew and a crane operator to hoist it into the air.
And then it doesn't fit.
And then it doesn't fit. It is an immense sunk cost. You either have to try and modify a structural component in the field.
Which sounds incredibly risky.
It's risky and it takes forever. Or you literally have to scrap the steel and start over.
But with rule-based clash detection, that hard clash is found in the model before anyone signs a purchase order.
Yes. The design team just adjusts the digital beam, reroutes the ductwork, and only then do they authorize procurement.
Saving exponential amounts of money. The cost of fixing it drops from tens of thousands of dollars on site to just the fractional cost of a designer sitting at a computer.
Precisely. And that physical predictability bleeds right into the next point.
Point 2. Sequencing conflicts are identified through 4D scheduling.
Because if you know the materials are going to fit, the next hurdle is the actual installation sequence.
It's not just about space, it's about time.
Right. Construction is this massive choreography of trades, drywall crews, electricians, plumbers, framers.
All fighting for the same limited floor space.
Exactly. Trade stacking. And a sequencing conflict isn't just, trying to put the roof on before the walls.
Right, the obvious stuff.
It's about scheduling tasks in a way that chokes the site's productivity.
Okay, give me an example.
Say the schedule calls for heavy machinery to pour a concrete slab in the north wing on a Tuesday.
Okay.
That entire wing is effectively inaccessible to anyone else.
Because it's full of wet concrete and heavy trucks.
Right. Now, if the 4D simulation reveals that an electrical crew is also scheduled to run underground conduit through that exact same wing on that exact same Tuesday.
Oh, wow. You've got a massive conflict.
And on a live site, that means the electricians are just standing around unable to work while the general contractor is still paying their daily labor rate.
But by simulating it dynamically beforehand.
The management team sees the bottleneck, they see the spatial footprint of the work, the staging zones, the equipment swing paths.
And they just restructure the choreography?
Ensuring a smooth flow of labor and eliminating the financial bleed of idle crews.
Which is brilliant.
Okay,
moving to point 3. Quantity mismatches are resolved through model-based takeoffs.
shifting from time back to materials.
So ensure you order exactly the right amount of materials based on digital truth, not a guess.
Because the traditional takeoff process, the way we estimate materials, is incredibly vulnerable to human error.
Someone literally sitting with hundreds of 2D drawings and a ruler.
Yes. Literally. An estimator manually measuring lines with a scale, calculating the required volume of concrete or the linear footage of pipe.
It sounds so tedious.
It's tedious and it leaves so much room for miscalculation. A slight misinterpretation of the drawing scale leads directly to a quantity mismatch.
And you underestimate the materials.
The project stalls. The supply chain scrambles to deliver a new batch, usually at a premium rush delivery cost.
And if they overestimate.
The project eats the cost of excess materials that eventually just end up in a dumpster.
But in a BIM environment.
Because it uses parametric objects, the model already holds the exact mathematical truth of the design. A digital wall knows its exact area and thickness.
So you don't need the ruler anymore.
No. Model-based takeoffs replace that manual measurement with a simple automated data query. You extract the precise quantities directly from the model.
Assuming the model is clash-free, the material order is mathematically certain.
Exactly. You procure exactly what you need, nothing more, nothing less.
That brings us to point 4, and this is the one I find really fascinating. The human element.
Yes.
The text points out a critical psychological shift here. Coordination meetings transform from toxic blame sessions into data-driven problem-solving.
This is perhaps the most profound change of all. The psychology of a traditional coordination meeting is notoriously adversarial.
I can imagine.
When a massive spatial conflict is found on a live site, progress stops. The financial pressure spikes immediately.
Everyone starts sweating.
Right. The architect, the structural engineer, the general contractor, the subcontractors, they are all pulled into a room. And the overriding instinct is risk shedding.
Pointing fingers.
Exactly. It's an exercise in self-preservation. The mechanical contractor blames the structural drawings. The structural engineer blames the architectural revisions.
Because whoever is at fault has to pay for the massive rework.
Right. Everyone is aggressively trying to avoid the bill. It's a high-stress, defensive posture that completely fractures the team.
Okay, contrast that with a BIM coordination meeting.
It's night and day. These meetings happen months before the site is even prepped. The team is gathered around a screen, navigating the digital model.
So when the clash detection flags a major intersection between, say, a beam and an exhaust shaft,
The atmosphere is entirely different. No physical materials have been purchased yet.
no labor has been wasted.
The financial risk is still dormant. The software simply identified a geometric problem that needs a solution.
It externalizes the problem.
Yes. It's no longer a debate about whose field team messed up. It's a shared focus on a data point. The conversation shifts from who is going to pay for this to how do we route this shaft around the beam.
It completely changes the culture of the project.
It provides a level of psychological safety. The different disciplines can actually collaborate. They can test rerouting options in real time, instantly verifying the new path against the clash rules.
Operating as a unified problem-solving entity instead of warring factions. Which really brings us perfectly to the ultimate goal described in the text. The summary here is fantastic. The whole point of leveraging these digital tools is ensuring the project team gets to laugh with the model instead of the physical site laughing at their drawings.
Finding a disastrous conflict while it's just rendering on a monitor is genuinely a moment of relief.
Oh, I bet.
You look at the 4D simulation, see that a crane is about to swing right through a newly framed elevator shaft, and you can just recognize the absurdity of it,
You fix the schedule, update the model, and crisis averted.
leaving the physical chaos behind.
The insights conclude with some really punchy mic drop quotes from the text. In modern construction, building without coordination is the real prank, not a fake spider in your coffee.
It's so true.
With BIM, quote, the only thing getting fooled is the risk.
That phrase perfectly encapsulates the value proposition. BIM is a system designed to actively hunt down and eliminate risk in a virtual space, making the physical execution as flawless as possible.
The text even includes a few key hashtags as a fun nod to the digital nature of all this. Let's see, hashtag April Fool's Day, hashtag BIM, hashtag clash detection, hashtag digital construction, and the big one, hashtag build smart not lucky.
Because relying on luck or last-minute adjustments just isn't a viable strategy anymore with the density of modern infrastructure.
Absolutely not.
Oh.
Well, we have covered immense ground today, dissecting the transition from static 2D drawings to parametric 3D models and 4D simulations.
It completely revolutionizes how we handle space, time, and materials, but I actually want to leave you, the listener, with a broader application of these concepts.
I don't like this.
We've spent this deep dive analyzing how rule-based algorithms and chronological simulations completely eradicate catastrophic surprises and toxic blame sessions in skyscraper construction.
Right.
But consider the complex, uncoordinated projects in your own life. Your professional life, your business, your personal initiatives. How often do we operate using legacy workflows, letting different departments or even different aspects of our own lives function in isolated silos?
Just hoping it all lines up.
Exactly. How often do we wait until a hard clash happens in reality? A severely blown budget, a massive scheduling conflict, a total breakdown in communication, before we finally sit down and try to resolve the issue?
Wow.
If we apply this philosophy of building it twice, if we simulate our plans and rigorously test them for clashes in a low-stakes virtual environment before committing our actual resources, how much smoother could our own complex initiatives run?
That is an incredibly sharp way to view our own workflows.
It's a powerful framework, systematically shifting our energy from managing chaotic mistakes during execution to preventing them entirely in the planning phase.
Taking the rigorous data-driven coordination required for a skyscraper and applying it to how we architect our own lives. I love that.
Yeah.
Well, that brings us to the end of our deep dive today. We want to thank you, the listener, for joining us, for bringing your curiosity, and for diving into the mechanics of the built world with us.
It's been great.
Keep questioning the systems around you, keep challenging those outdated workflows, and we will catch you on the next one.